Hello everyone. In this video, I'm going to have a discussion with the creator, the original creator of Symbolic Python, Dr. Ondřej Čertík. Symbolic Python, or SymPy in short, is a library of open source programs written in pure Python. It can be used for a number of different purposes: algebra, solving different kinds of equations, linear simultaneous equations, differential equations. It can be used for calculus, for linear algebra in symbolic form, and a bunch of other things like number theory. It is used mainly by scientists, engineers, and certainly mathematicians. I, for one, use it regularly in my courses of elasticity and mechanics of solids. My students also use them regularly while doing their term projects. In fact, SymPy makes our life in elasticity and mechanics of solids a lot easier. On the development side, SymPy is being actively developed by a growing community, a lot of whom are Indian students, and many of whom have been directly mentored and trained by Dr. Ondrej Čertík. Beyond SymPy, Ondrej is also involved with a number of other exciting projects about which we are going to have a discussion. What follows is a long and elaborate conversation with Ondrej. I hope you will enjoy this conversation as much as I did. Hello, Ondrej. A very warm welcome to my small YouTube channel. And thanks a lot for sparing your time to be here.
Hi, Jivan, and thank you for having me.
Hello. So we'll start off with the questions immediately. So Ondrej, when did you first start learning how to program? What was your first programming language? And if you remember, what was the first program that you wrote?
So I learned the program I started when I was 7. I think my dad was teaching. 7, yeah.
Oh.
My dad teaching me how to program, and I think my first program was incrementing a variable, and it was in Pascal, Turbo Pascal to be exact.
Okay. I've never touched Pascal in my entire life. The first thing I started learning was BASIC. I think many people from my generation, they started learning in BASIC in this school. Okay, so next question is, you are the creator of SymPy, right? And SymPy, as far as I understand, is written in pure Python.
Yes.
So when did you first start learning Python? And what was your experience with it like initially, so that like you felt an intrinsic appeal to it that you actually went ahead and used Python to create something new altogether?
So I think I first learned Python while I was still at high school. I think it was in the early 2000s. I don't remember exactly when. And what I liked about Python is that it was a language that was a general purpose language. It was not tied to any particular application, such as, let's say, Mathematica or MATLAB or only web development or scripting. It was just meant as a language that can be used for anything. And it's open source, easy to install, and it was easy to write extensions, either pure Python libraries or even C libraries or Fortran libraries, and wrap it so that you can publish your code, your library, and then people can easily use it from an interactive environment.
So was there like a programming culture in your school, something, or was it completely on your own?
It was completely on my own. I discovered online.
Good to know. So you mentioned, I think in passing, Mathematica, right? So that was actually my next question, that what was it exactly that motivated you to start the Symbolic Python project, the SymPy project? So did softwares like Mathematica or Maple have any influence on your thinking?
Yes, so I used Maple and Mathematica and MATLAB at high school and kind of late. I was having some internship at university, and those are the tools that they used. And I liked Mathematica a lot. It's just that I wanted to be able to tweak the algorithms. So I wanted to have access to the source code of, let's say, the algorithms, how it computes things, so that I can tweak it, and also so that I can write a script or kind of an application, if you will, that uses Mathematica as a library, and that's open source, so that people can just download it and run it on their hardware, on their computers, without any issues. And with Mathematica, you cannot do it, because if I distribute my script to somebody, they have to buy a license. So it's a whole process before they can run it. But with Python, all they have to do is just literally download, and if they use Linux, they can just run it right away. And so the barrier is just much lower in Python. that's kind of, I think, the main kind of advantage that I liked. And also, as I mentioned, I think the language is slightly nicer. I like the Python language. It's a very simple language, very quick to learn, has very few ways that you can, be surprised as a beginner with Python. While with Mathematica, it has all kinds of corner cases where you have to kind of get used to it.
Thanks. So this was on the environment side of things. Purely on the mathematical side, where was there some kind of a motivation that? So
yes.
maybe you were trying to do something in Mathematica or Maple, and then you felt that perhaps if only you could tweak the source code a little bit, but you couldn't, and then you thought that what if you just started the whole thing from the groundwork in a completely open fashion, you could lay the groundwork yourself, tweak it as you wish, something like on those lines.
Yes. So one of the first, so I was studying physics at the time, and so one of the first kind of places where I really wanted to have something like SymPy is when you do general relativity and you are trying to derive the Schwarzschild solution from the metric for it from the Einstein's equations. It takes, especially if it's the first time you're doing it, it takes like 3 hours of derivations on the paper, and it's all relatively very simple, just a symbolic for matrix, and you differentiate pretty much, and and just add terms together. So it's just something really simple, but if you do it by hand, it just takes forever. This particular thing you can do in Mathematica, but what I wanted to do is have a Python script so that I can have the matrix, symbolic matrix, as a Python variable and be able to print it and kind of play with it from Python. I mean, Mathematica is perfectly fine product. I think you can do anything SymPy can do, and anything, many people use it all the time. But I think I just kind of like the Python. I like that, as I mentioned, that you don't need any license. It's all open source, all available for me or others to easily play with. So that was, I guess, my kind of initial motivation. And of course, as a physics student, so much stuff that just is asking for being automated and making it accessible from Python.
So it was a similar sort of experience for me, except that I used what you and the other contributors had created. So back in 2019, I was teaching a course on elasticity here at IIT Kharagpur, and so there was this entire derivation in 2D polar coordinates. So where we had to go from the Cartesian system to the 2D polar coordinates, and the entire Laplacian had to be derived in terms of the r theta coordinates. Now we have a very famous book in elasticity, like an all-time classic by Timoshenko and Goodyear. So all the steps are mentioned there, but in a very Soviet fashion, they skip all the steps in between. They give the very terse kind of results. Now, I did the entire thing by hand. It turned out to be 10 pages long. Now, I could not do that on board. I mean, I could do that. I would have to invest 2 weeks of my class hours. So I thought that what if I just try to do it in SymPy, like see for myself if I could do it. It turned out like I could do it very quickly. So I thought, why not just demonstrate it in class for the kicks of it. I demonstrated, and then the feedback was so nice then that I continued to use Symbolic Python for the rest of the course. And then in the subsequent years, I have actually went on to encourage my students to do their term projects also with Symbolic Python. So that makes the course a little less boring. And I think we have all benefited. So thanks a lot, actually, as a teacher myself.
Yes, I mean, you are kind of coming from the same, it's effectively differential geometry, whether it's geometry or not fly is the same thing. It's just some kind of effectively matrices, and you have to transform from one coordinate system to another, and so it's a lot of work.
Yeah.
And it's people used to do it by hand. That was the only way, but it's just one of the things that, as a student, when you really want to learn it, you really kind of have to do it yourself. That's the only way to learn it. But because it's so tedious, it just is very discouraging. But ideally, if you can just take a symbolic package like SymPy and just write the code yourself so that you know exactly what the steps are, but automating them, I think that's the best way to learn. And a lot more fun. Let's say with the general relativity, you can change the metric and see how the equations change, see how things change, and just kind of very quickly. You don't have to wait 3 hours and make a mistake and then just takes forever to track it back. So you can kind of play with it and really get good experience and realize, oh, the ideas are super simple. It's just the mechanism, to do these transformations it's a very straightforward, very simple, idea. It's just tedious.
So thanks for actually mentioning that, because I had noticed that this tediousness or the tedium of actually going through that algebra and the demotivation that arises from just making a sign mistake here, or maybe a sine theta becomes a cos theta somewhere because of a certain lapse of concentration and the whole thing goes wrong, and then you never get around to deriving it yourself. But that is something which every student, by the time they're undergraduates, they can do. They don't have to prove themselves to it on a weekly basis that I can do it. That's done and dusted. But what I think they can spend a better investment of their time would be to actually outsource this thing to the computer, which is very good at repetitive tasks, and to actually use our precious brain time to understand clearly those critical junctures of the derivation, because that's what really matters. Instead of being careful with the plus and minus and the sine theta and cos theta.
I mean, and you can even generalize it. It's not just the symbolic derivation. It's also, as a physics and your background, the same thing. You want to solve ultimately the equations, and typically numerically. And so to actually write programs to numerically solve those equations, even if it's just a very simple, something you can do yourself, that's the best way to learn it, to actually get the correct result, convince that you are getting the correct answers. Then you can say you truly understood everything. And so the symbolic part is part of it, to actually get the equations in the first place. And then the second step is to actually implement them numerically.
Yeah. Plus, there is also the thing that once you have that a few scripts ready, you can keep on reutilizing them. So it's like something like, okay, I have built it myself. It's my own thing. I don't have to keep proving to myself that I can do it again. I have done it. Let me reutilize it. Okay. Yeah. Okay. So lingering a little bit on your early days. So your basic training was in mathematics and physics. And you were, I think, an undergraduate student when you first started writing up Symbolic Python. So at that point, did you get some kind of mentoring? Because I'm sure Google Summer of Code did not exist back then, right? No. Yeah. So you have been a mentor to a lot of students, and we'll come to that. But at that point, when you first started learning, first started writing up Symbolic Python, did you have any mentors, or was it just on your own?
My own, yeah. I graduated high school. I went to study physics, undergrad, so it's just a general physics. So the classes we had is all kinds of physics and math classes, as well as experimental physics, like labs, I guess it's called in the US, which I did not enjoy too much. By the way, it's a tangent, but I love the physics labs to do the measurements. It's always fun. And I did enjoy kind of interpreting it, but I hated writing it up in reports. It always took forever to my favorite, but anyway, so I loved. I mean, if I did it again, I would do exactly the same thing. I would still study physics. I think it gives you the foundations to everything. Regarding programming, I learned that at high school, as I mentioned, my dad helped me when I was, and then from then on, I just kind of learned on my own as I could. And then at high school, I was pretty good at it. And at university, I just kind of learned everything on my own. So and so starting SymPy, so I knew Python. I knew C and C++, a little bit of Fortran, and I knew a lot of Python, and so I just started doing it, I guess.
So a lot of the good institutes, certainly we have that culture nowadays, but back then, so this was around 2004, 5, something like that. I think you are just a year older than I am, like in actual physical age. So I think it was around that same time. at your institute, I think it was the Charles University in the Czech Republic.
Mhm.
Yeah. So did that institute have some kind of a programming culture?
So they have a computer science department, but I studied in the physics department. And so we had, I guess, one class in the very first semester, I think, for programming in Pascal, I think. And that's it. That was it. Well, actually, I guess later on we had some numerical programming later, but mostly I guess, yeah, I guess we had some classes, but it's not enough to, it's just a very kind of intro. I guess it's not enough to, you have to learn it on your own, I think. And I mean, I guess I never felt that I need the computer science classes to learn how to programming. I think the best way to learn programming is to sit down and start programming. It's not, that I think is not the hard part. The hard part is to know the equations. I guess for physics and engineering is to know the equations and the math, and that's something that's extremely hard. At least what I found out for myself. Learning the programming part is easy. The hard part is to learn the physics, and that's something that's extremely hard to learn on my own because it's a lot. It's completely overwhelming, and it's tough to kind of even know what to learn and so on, and it takes real investment. And so that's what the university really gave me, is the physics and math background. The computer science, like the technical programming task, I think anybody can learn it. It's not that much to it, I think.
So you mentioned this on your own. I was about to ask you. So your entire undergraduate formal training has been in mathematics and physics. So also your master's, and the kind of projects that you did, the actual scientific projects, those were, I think, in the general area of chemical physics.
Yeah. So I guess every student chooses their own. I always wanted kind of computational, numerical.
Right.
Yeah.
So at that point, you were doing your actual scientific project work and at the same time developing symbolic Python and things like this?
Yeah, so during my undergrad, you have to do a bachelor thesis, I think. So that's a project.
Right.
Well, some classes require projects. Yeah, so that's the usual school work. I think that's everywhere kind of the same. And then in addition, in the evenings and nights, especially, I was working on SymPy, yes.
You must have been a very, very academically serious student.
Well, I mean, so during the batch, so I guess when I entered university, I was, well ahead in physics and math. And so I kind of took, very quickly the advanced classes. So the bachelor, I kind of got out of the way pretty quickly. So in the third year, I actually had so it's only 3 years in the Czech Republic. The bachelor is only 3 years. So in the third year, I had a lot of time, I think. So, I was kind of focusing on SymPy. What it got me in trouble is during my master, because then I kind of did not realize I studied theoretical physics. And so what happens is that the bachelor, as I remember, is relatively easy. It's not much, just kind of basic physics, basic quantum mechanics and all the math and so on, but it's not that difficult. The difficult part, which I wasn't prepared for, comes during the master because I studied theoretical physics. And so that's when the general relativity and quantum field theory comes in, not just intro, but the actual, and it required a lot of effort to pass. And so I almost failed university because I was focusing on SymPy, and I thought, yeah, this is kind of easy, and then didn't realize, this requires a real effort to learn. So yeah. So anyway, yeah, I guess my schedule back then was I pretty much did my classes I think in the afternoon, and I came home, and then just in the evening just kind of worked from 6, let's say, or 8 p.m. till 2 a.m. or sometimes 4 a.m. or even 6 a.m. depending on the day. And then I slept till noon, let's say, and I went back to university for a couple of classes in the afternoons, and that's kind of how I did it. So I remember, so I started SymPy, and then I just kind of did initial, let's say for a month or two, I kind of initial work, and then I kind of let it sit. And then a person from Spain, his name is Fabian Pedregosa, he just started contributing. And so so when I saw somebody actually contributing to the code, I thought, well, then that's it was a lot more encouraging to work together. And so we, for maybe a month or two, we worked really hard on this. And then I signed up for Google Summer of Code. So we had I think 5 students the first year, and that's how it kind of got off. It took off, and after that, I worked really hard on it. I realized, oh, this has really huge potential. And so I worked really hard on it for half a year to a year, pretty much every day, every night. So doing the school, and then I came home and just, worked through the whole night. It's kind of, back then it was easy because night is quiet, so I can focus on on it, and no interactions, no disturbance, and so I can really focus on give it the hours that it needed. And then once the project is advanced enough, then it kind of, the ball eventually starts rolling on its own. But the hard part is to get it there. So that's why I did it.
So does that mean that after your master's, you kind of took a break from everything else to focus on SymPy development?
No, well, no, I kind of did it during my master. Almost failed the university, but then I kind of got back on track, graduated, and then I came to the US to do my PhD. And
so
then
this was at the University of Nevada at Reno, right?
Nevada, Reno. Started PhD in chemical physics, and then I think the first year or two I was also working pretty hard on SymPy, and then eventually I had to then. At that point, it was already doing really well, so it didn't need me as much, and then I had to then stop working on it to focus on the PhD to be able to finish it. So then once you start writing, I'm sure you know the thesis, that you really have to focus, focus your mind. And so I kind of gave up all that and really focused to get the PhD out of the way. And after that, I guess I then got a postdoc and a job. And so I kind of work with SymPy as a mentor, and as well as helping organize and the financials and so on. But the day-to-day activities, I wasn't as involved.
So please don't mind me asking this. So we have heard of these stories. So people make movies and like they hype up these kind of stories where people make something from the software world and then they drop out of university. Which I personally, as a professor, I cannot support that kind of behavior. So it's quite encouraging to hear your story that you were doing this, but then you always kept getting back on track and finishing what you had actually started at university.
Yeah, I encourage the same thing. Now, things might be different if I was born in the US, because the opportunities here are, very tempting and of course much bigger. But in the Czech Republic, the only way to get, for me to have the career that I wanted, the only way is to finish the schools. You cannot drop off, because then it just kind of closes the doors. So, but yes, it's extremely tempting, because it's if you do something that's impactful,
right?
Has a meaning. Let's say the SymPy in my case, then it's very tempting obviously you kind of ask yourself a question: why are you studying at all instead of focusing on this full time? But my approach was to get the schools out of the way while I'm still young, because as you get older, there's just no way I would do another school like that, because that requires a lot of time, which I had when I was young but don't have anymore. And so I knew that. So I knew that I cannot, like, when it goes really close to being to be able to, really close to dropping out, I realized, no, I really need to focus on the school and not get myself kicked out. So
did this kind of a thought play a role, maybe a part of the role at least, that you were engaged, at least at that time, in something like Symbolic Python, which has its utilities primarily in the physical sciences, arguably. And you were, formally a student of physics. So it would be like kind of betraying your original, your mothership, if you abandoned physics. And probably, I think in the longer run, that has stood you in good stead, right? So your completed training in physics, maybe that informed your work in Symbolic Python. So maybe I'm just guessing here. Okay, so correct me if I'm wrong. So probably that helped a little.
No doubt that's the physics or engineering too. Your background is very similar from this perspective. It's very, I would say, applied from the computer science perspective. Like I was always interested in the actual, results, I guess,
Yeah.
as well as I'm interested in maintainable software as in kind of an engineering product. But I've never was interested in kind of abstract math or abstract something that's not really applicable. And so from the SymPy, so there's a lot of, so when I started at SymPy, there are a lot of, even back then, a lot of other libraries, even open source libraries, such as Maxima, Axiom.
Maxima is open source?
Mhm.
Okay.
Yeah, it was already open source back then. But a lot of times, let's say with Axiom, it was tremendously powerful in terms of it had some really, geniuses working on it. So it had integration, for example, for integrals, one of the best, ever, even for commercial software. But it always was just kind of tailored a lot of times to kind of abstract things. It wasn't as easily applicable to, basic tasks like SymPy is. And Maxima is very nice, actually. Maxima is, I think, applicable, except that it's written in Lisp. And I tried.
Oh, man.
I'm not against Lisp or anything. It's just that it's hard to kind of understand it and modify it. I tried. They had some bugs and limits, and I tried to go in and to code and see if I can fix it. But it was really hard for me to get into it. And so the barrier, I would say, to entry, to contribute, is really high. And that you were asking why I chose Python. I think the barrier to contribute to Python is really low. It's like anybody can learn it quickly, and it's kind of natural, intuitive. And Lisp is just not intuitive to me, at least,
Right.
So
probably we can circle back to this thing you mentioned about the lower entry barrier to Python. Does that, if you could just linger on that a little bit, do you think that has something to do with the way the language itself is designed, meaning that it's somewhat closer to the way that we as human beings tend to think? It's a little bit less punitive, or perhaps a little bit more forgiving to our loose way of thinking as human beings. When we learn to talk, we make certain assumptions that the other people will pick up on certain unsaid things. So Python probably is a little bit more forgiving on that account, and so a little bit closer to the way we think as human beings. Do you think that's true, or maybe?
yeah, I think it's a lot for somebody who's not an expert in programming, maybe complete beginner or just just a beginner. I think it's a lot easier. You just kind of tell it's imperative, so you just kind of call some functions and create some arrays and do some computation, and it's interactive, so you can interactively see the answer right away, and you can explore the answer. So you can kind of explore the what you are trying to compute, and kind of iteratively do exploratory work and arrive at something that almost works or ultimately works, and then you put it into a script. And so I would say this kind of workflow is very, very good. Mathematica has a similar workflow, MATLAB also, and I think this workflow is very good. And I think it's very kind of good for beginners. I think Lisp is fine. A lot of people like Lisp, but it requires investment, I guess, to learn. And so if your background is physics, for example, or engineering, I think the barrier is higher. Intuitively, it seems to be. For me, at least it is. Let's put it that way. For me, it was. And so that's why I chose Python. But I think a lot of people are like that as well.
So after your PhD, I think you did your postdoc at Los Alamos.
Yeah.
And you stayed there for quite a few years, right? Until quite recently. So
Yeah.
what was your experience like at Los Alamos? Like it's a legendary place in the public in the public imagination. The Manhattan Project, the atom bomb, and the entire stories that Professor Richard Feynman had narrated in his books. So it's a very mythical place for people outside it.
Yes, it is. Yeah, absolutely. And so it's very nice to be able to spend and work here. And I recommend the place if any.
That's
place.
good. Recommend the place.
It's a big lab. It's about 10, I guess 13,000 people now. Not they did a lot of experiments, but even in computational science, let's say where I was, at least thousands of people, and so you'll get to collaborate with a lot of people, just hundreds, and very smart people. Very like I learned a lot every day. I learned something, and it's from I enjoy computational physics, computational science, and Los Alamos is a great place for that. That's what I was doing every day in some aspects of it, and also the history, and they have archives you can go and see, and it's for me intellectually it's very satisfying, I guess, and it is a famous place. It's nice to talk to if you talk to some of the older people here, they remember some of, let's say, Edward Teller, and stuff like that. So you can talk, it's kind of those, Edward Teller, those people are long dead, but people who knew them as colleagues, some of them are alive, and so it's nice to be able to talk with them and meet them and so on. And it's I after getting my PhD, the options are either get a job in industry, or go to academia, or go to a national lab. A national lab is something in between academia and industry, so it's much more applied, has a mission. You don't have to typically apply for funding, but you have to be doing what the mission is. So it's not that you have a freedom like in academia to do anything you want. You have to be doing what something that the lab needs to get done. But because it's a big lab, there are a lot of projects, and so once you get to know enough people, there are so many interesting projects you can find and work on. So from this perspective, you have to kind of find. I think it's similar at any big corporation. Once the corporation is big enough, there's always some nice, very interesting projects. You just have to get to know the people and convince them to fund you. But otherwise, to get you in the project so that you can work on it. But so I recommend the place.
So is there some kind of an incentive on the employees there or the scientists, more appropriately there, to obtain some kind of funding, like professors are expected to in a research set in a research university setting? Is there some kind of an incentive or requirement for the scientists there to bring in funding on their own? People who work at Los Alamos or similarly in other national labs?
I would say, it depends on what you want to do. So if you want to propose your own research, then you have to figure out how to fund it. So there's multiple ways to get it funded. There are some internal grants so you can apply for. There are outside grants. In the US, I think it's the Office of Science and DOE, you get those grants. You can, I think you can bring industry funding too. If you have contact and convince the industry to fund some research, you can do that too. And then if you don't want to bring your own funding, then typically you would work with existing projects. And because it's a big lab and a lot of projects, there's always some, it depends what you want to do. But like, let's say in my case, I wanted to do computational, physics, electronic structure, as well as kind of the big multi-physics codes and learn some of the methods and so on. And also I enjoy kind of doing basic research as well as applied. And so and my approach was kind of open, and so I always found a lot of interesting projects to work on in here.
So SymPy was your baby, right? And you are now in a national lab. So did you get some funding on your own? Or was that kind of encouraged for further development of SymPy and your other projects? So we will come to a discussion on Fortran and LFortran, the work that you've been more recently doing. But did you get some funding on that? Or?
I was hoping to get, but I did not figure out how to do that. So no. And I think kind of interesting thing. Almost every group, the computational groups in Los Alamos, there's at least one person who uses SymPy. So that was very. But typically they use it maybe once a month, to compute some stuff, but they don't use it on an everyday basis. And so it's hard to then fund the development for something that you use once a month. And development of SymPy, just like any project, requires it needs to be a full-time job. And so one approach that I thought is to kind of get little funding from multiple projects and kind of patch it up together, but it's hard to do in practice. So I did not succeed. to get it funded or to get funding for SymPy.
All right. So regarding the development outside this structured environment, so beyond the university, beyond this national labs, so there has been an ever-growing presence from the open source community contributing to Symbolic Python, as well as other projects that you've been working on. So through this process, you have been a mentor to many students, and quite a few of them have been from India, especially for Symbolic Python. It just so happens that many of them have been from India. I think quite a few of them from the IITs also. So how did it actually come about? Why is there such a bigger presence of Indian students, specifically in this particular project of SymPy?
So I don't know. I think that I don't know. I think it probably India has a lot of students, a lot of I don't know. It also, I think the money that you get, let's say for Google Summer of Code, used to, and I think it still does, get quite far in India. So it's in terms of, I guess, for somebody, let's say from Europe, it's not, doesn't go as far. So that might be one of the reason. But it's more to it. I don't know. It might also be that once it kind of starts, then the younger students see the older students, and it's just kind of a culture.
That's one of the big reasons. Because I mean, if we extend that argument, then we have sufficient students to contribute equally to NumPy and the other open source projects, but we don't see such a big presence of Indian students.
But I think in general for Google Summer of Code, there are a lot of students from India, even in general.
Yeah, right. Yeah, but within the Python ecosystem, I think it's like a disproportionately high number of Indian students in SymPy, right?
Yes, but I think that might also be because I realized that this is a very nice way to get a lot of good work done, and so I recruit students, and then they become mentors next year, let's say, and just have a lot of collaborators that way. And so I enjoy working with students, and so I always spend a lot of effort to make sure that we have a lot of students every year. And if you don't put the effort in, then then you don't get students, I guess. So maybe that's also part of it.
I really think so. I mean, those are the main two reasons. Like after a student has gone to a certain mentor, and if the experience has been good, that information gets passed down over generations. So that kind of feeds back over the years and creates a snowball effect, I think. So do you want to mention something about the Google Summer of Code? So I think even beyond Indian students, you have had some excellent contributors, some long-term contributors that you initially met through the Google Summer of Code. I think the current lead developer of SymPy, Dr. Aaron Moyer, I think, I don't know how to pronounce his name. Aaron, yeah. So I think he was through, you met him first through the Google Summer of Code, right? In 2007, was it?
So 7 or 8. Yeah. He stayed the whole time, and when I was focusing on my PhD, I realized I have to find somebody to take over, and he was the most natural, the most active and excited and young and everything. So I figured, I'm just gonna go with it, and he's done a tremendous job. In fact, when I just said, from now on you are the main person, he just SymPy flourished. He just, that's, I think when we got to the Google Summer of Code as our own organization the first time, and he really just took SymPy to the next level. So that also taught me a lot of lessons too, is that like you do something for a couple of years, but you kind of done the 80% that's easy, and then the rest 20%, it can take the rest of my life to get, and I might never get that. If I kind of pass it over to somebody else, they can then take where I got it and just bring it much further than I ever would. So I'm actually very happy with that I've done that so early, because I would not be able, SymPy would not be here if I did not do that, because I would not be able to. I have strengths and weaknesses, and he just kind of complements beautifully, and so it was a great choice. Yeah, so that's Aaron, and I guess I met so many great people through just the Google Summer of Code. It's a nice, the Google Summer of Code is nice that it allows you to just meet people you would otherwise not meet. And so I have a lot of the early students I'm still in touch with. Mateusz, for example, from Poland was another one. He implemented, I think that was from 2007, and he implemented all the polynomial support and all the integration, all the difficult polynomial factorization and stuff like that. And then, we just kept in touch over the years, and just like that with many other students. And so, yeah, so it was very enjoyable.
So Aaron, I think, is a maths PhD, right?
I don't know if he has a PhD, but yes, at least he's a math student, master, I think.
Math student, okay. So I think that really very well complemented the kind of input that you had initially given in SymPy. So from the physics side and then from the math side. So the stars are actually lined up for SymPy. Okay, so my next question is that we have been talking about SymPy quite a bit. Let's now move on to some of the very, very interesting work that you have been doing, not recently, but more recently compared to SymPy, on Resurrecting Fortran. Now, for nerds like us, I think there's a movie there, but we'll get by with your story for now. So tell us the story of how you are resurrecting Fortran.
Well, so as we discussed, to be able to learn something, you have to actually either do it by hand, but preferably on the computer. And so for the symbolic part, SymPy is one of the choices. But when you want to implement something numerically, then you have different kind of choices. So you can use MATLAB and Python as well in NumPy, but has issues with performance. And also the other issue with that is if you just want to do a prototype, then I think Python or MATLAB is ideal. But once you want to have a code that you maintain over the span of days and weeks and years, even if you are the only developer, then I kind of over the years, I used to do it in Python, but over the years I kind of and now much prefer something like Fortran. And the reason is that it's compiled, so it's much more robust long term. With Python, what happens, the main difference between, let's say, Fortran and Python is that in Python, you have to have tests for syntax. So if you make a mistake, so Python itself parses the syntax, but if you, for example, use a variable that's not defined or mistype something, or more typically you refactor the code and you forget that something doesn't work anymore because it just doesn't align. Maybe you add an argument to a function and so on. Python doesn't help you at all. You have to have tests and you have to run the tests to discover that. And those can take a long time, especially for computational stuff, to discover that code path that fails. In Fortran or any other compiled language, the compiler catches 90% of these bugs right away and fast, quickly. Like the compilation, well, Fortran, first of all, is very fast to compile, but even C++, people say that it compiles slow, and it's true. But it's still much faster than running the Python test suite. And so even the C++ compiler gives you the errors right away compared to Python. And so the development experience is just much more robust for these long-running bigger projects. And then, of course, when you collaborate with multiple people, my experience with Python is that you get a pull request, but you have no idea what things broke, and it's hard to tell. So you have to run the test suite. But even then, it's kind of tough. With the compiled language, you just, as long as it compiles, that at least, every function has the correct number of arguments, the types match, like 90% of these easy, bugs are fixed, like, they are just not there. And you can focus on the functionality to make sure nothing got broken, as well as design. So that's kind of what I came kind of back down to. So first, you were asking how I started with Python. So what's nice about what I liked about Python initially is that, and I still like it, that how easy it is to get into, how easy it is to program in, and it's very powerful. But then I still like it for those reasons. But for kind of production, bigger codes, vertical codes, I kind of came back to compiled languages. And so then, what options do I have for compiled languages? Well, it really is not that many. For numerical, it's C++, that's the obvious choice, and then Fortran. Possibly Rust or Go and these languages, but we also performance. And so C++ is one option. You can decent performance out of it. Fortran is the other one. And what's nice about Fortran over C++ is that it kind of looks like Python. That really is, is maybe a little bit more verbose. You have to write subroutine instead of def, as in Python. But it's not that big of a deal. You get used to it. It has arrays as part of the language, and it really does look like the Python. It's just the only difference is you have to declare all the types. But as I argued, you want to do it anyway. And so, with Fortran, like stuff that you want to do anyway, you do, and then there's not much else there. And so it's not a bad language. Now, what I don't like about Fortran, or the reason Fortran is on kind of a downward trajectory is that the tooling is just not great. The compilers, packages in general, package ecosystem, and in overall just the state of the language, or I would say state of the ecosystem. But if the language is good, it's just the tooling that's not as great. That can be fixed, and so that's how I got into. And I realized the main thing that we need is a compiler that fixes most of the issues I had with other compilers, as well as makes the language interactive, so that it kind of looks so that you can use it like Python interactively from a Jupyter notebook or a terminal. So that kind of fixes the main issues I had with Fortran. Or once we deliver, it will fix those issues. The rest of the issues are things like running on GPUs, for example, and some platforms. Say, to give just one example that will perfectly illustrate what I'm talking about. Let's say you buy a new Mac computer. Well, there's no Fortran on it, and it's not easy to install. Actually, it's impossible to install. So, while if you want to use C++, then it's first of all already there. Clang is there, and even if it wasn't, typically the C++ compilers are easier to install. And so that that kind of illustrates exactly what I'm talking about. But those things can be fixed, and so. So that's how I got into it.
So, right. So in that little short paragraph that you just said, you have unloaded a lot of information. So let me see if I can chop this up a little bit, because a lot of the viewers of this channel, they are younger students. So let's linger a little bit on the historicity of Fortran. So Fortran predates the birth years of the majority of the students who would be watching this video. I think it predates mine too, right? It was first in the 60s, right? So it's older than both of us.
Older than that.
Yeah, older than that. Yeah, probably. Yeah.
94 or 5 or 3, something like that.
Yeah. So and the motivation from the very outset of development of Fortran was to apply it in the physical sciences, in mathematics, in engineering. So correct me if I'm wrong.
The initial motivation was to Fortran stands for formula translation. So to translate formulas into code. In the broader scope, to translate math or kind of computational math into code that is performing and that it runs on every platform, so that you don't have to write it in assembly and then you go to a new platform and you have to write it in assembly and rewrite everything. The idea is to write it just once and it runs everywhere, but it's still performing, very performing. So I think that was the idea. I mean, assembly back then, or even today, if you only have one platform, it's actually not too bad. I mean, you can, yes, it's maybe it looks harder, but you can learn the instructions and eventually do a program. But the hardest is that you go to a different platform and you can throw it; it will just not run. And so the key is to be able to do a much higher level language. And also, I guess, up until recently, I would say the Intel x86 platform is just an absolute, like pretty much the default. But back then, every computer had a different instruction sets. And so having a language that compiles to all these computers is a huge win.
That was a big deal back then, right? Plus, as you mentioned, the full form was formula translator, right? I didn't know about that. Yeah. So I mean, I think that directly tells us that it was meant for the sciences, right? So which is why scientists and engineers took naturally to it.
It was always meant from the beginning, but let's say if we come back to modern Fortran, it's meant for array-oriented scientific computing. That's where it shines.
Right.
The purpose If that's your goal, then Fortran is a good choice. If that is not your goal, if, for example, you want to do some string processing or web development or write an operating system, then I would say don't, or a compiler. I would say don't use Fortran for that. But if your goal is scientific computing and kind of numerical, not symbolic, numerical computing, then I would say Fortran is a great choice.
Right. And I think it's important to make a distinction between numerical computation and symbolic computation. So we were talking earlier about symbolic Python, which has its own strengths, but Fortran by design is absolutely great for numerical computations, very robust, very stable. Yeah. And it has a long history of excellent libraries which have been contributed over the many years for proper implementation of the actual mathematical algorithms.
LaTeX is probably the most famous. The API is still used everywhere. Even the OpenBlast, which is I think the most used open source fast implementation of the matrix operations, it still has Fortran in it for historical reasons, and assembly for the fast implementations, but Fortran for the higher level functions.
And I think, correct me if I'm wrong, I think MATLAB initially was, the backend was, a lot of it was in Fortran, right?
I think MATLAB, if I'm not mistaken, began as they took Fortran but wanted to make it interactive. Right. Kind of like Fortran, but back then they decided, we'll have our own language kind of inspired by Fortran and powered by Fortran underneath. And if I'm not mistaken, I think somebody have found the original, or maybe the original source code of MATLAB, I think is online and now available. And I think it's in Fortran. And I think on the Fortran discourse forum, if you go to fortran-lang.org, there is a discourse forum. I think you can find a link to it. And I think people try to compile it and play with it. So that's how MATLAB began. I think.
I'll get back to you if you can share that link. Maybe I can share with our viewers. That'll be interesting. I think, but now MathWorks have ported entirely to C++, right?
Yeah. Or Java, I don't know what they use.
Right. Okay. So you also mentioned something about the interactivity of Fortran, which was largely missing. I mean, the MathWorks guys did something about it, but in a completely different way, than their own way, and very logged in a proprietary way. But your more recent work has been developing something called LFortran. So could you please tell us something about it?
Yes. So the initial motivation was that I want to develop some new algorithm. So I typically use Python and NumPy because it's very easy to do exploratory work and do plots and so on. And I've done it many times, and then I have to copy that Python code into production code. So either C++ or Fortran. So let's say Fortran. Well, and so you make mistakes while you manually translate the code, and then you have to debug it again. Right. It's just so inefficient way to do that. It would be better to do everything in one language. And so if Fortran is the target, then making Fortran interactive so that I can do this exploratory work with Fortran itself, even possibly calling some of the production codes, modules to set up a mesh or something, get the matrices exactly as they are, maybe in production, and then just do some. I think I was coding some eigen solver, specific for the problem. So that was the initial motivation, realizing, if we can make Fortran interactive, then I can just code it in Fortran, and then I have it. I don't have to, I can just copy and paste it to the production code. I don't have to translate. So that was the main motivation to make Fortran interactive. But while doing it, I realized, I can also fix all kinds of other issues that always bugged me as a user. And I think they can be fixed. One of them is, let's say, the compilation speed. So Fortran compiles generally much faster than C++, but still, once you have a big code, 500,000 million lines, it can take quite a bit to compile. But why cannot it compile faster if you have a faster compiler that compiles faster? So I designed LFortran. I spent a lot of time designing it to make sure it can compile faster, so that the internal data structures are very fast to construct, very fast to visit. And the other things that bother me is, I would like the compiler to help me with the things that compiler knows, such as, so Fortran, for historical reasons, has all kinds of design choices that are all right, but people make mistakes. So for example, when you write 1.0 in Fortran, it always means single precision floating point. So, and then when you assign it to a variable that's double precision, typically you want to use double precision. Well, it will pretty much give you random digits in beyond that single precision number. So for example, if you assign like 5.5, you get 5.5, then 4 or 5 zeros, and then random, just random numbers, whatever was in the memory. So that's terrible. You don't want that. And so the way, of course, what is recommended is to always specify the precision of the constant. So write it like 5.5, and then underscore, and then DP, where DP stands for double precision, for example. But the problem is if you forget, and I've seen it all over production codes, just, most of the time it is like that, but sometimes, people forget. And then you get you're losing accuracy just by this. Well, why cannot the compiler warn about this? And not just warn, just disallow it. Why cannot the compiler say, just by default, just not even allowing this, and say you have to specify the precision? That would eliminate these bugs completely. And this is just an example, but there's dozens and dozens of things like that the compiler can completely eliminate just by not allowing it. And of course, you have to have compiler options to disable it, but the default user experience, what I would like from a compiler is to be kind of like Python, just give me good error messages, disallow things that I don't want in the first place, and just make the language completely safe. And that's completely doable. So with LFortran, that's kind of our approach. Or another example, historically, Fortran, because it evolved over 50, 60 years, it did not have, sometimes it has multiple ways of doing things. So for example, when you do a less than operator, so in modern Fortran, as well as in Python, you just do the less, angle bracket. But in F77, or at least, you had to use dot, LT dot, and both are supported. So with LFortran, we already implemented it. We just give a hint. We say style hint, and we say use, in modern Fortran, use the angle bracket. And so by giving hints when you compile your codes, I think we can completely pretty much modernize, because nobody wants to get warnings. And so if these are by default, then users will realize, oh yeah, I should just use that. It looks much better anyway. And that way they can kind of modernize their codes, kind of painless. It's kind of painless. You can ignore the warnings, it will still run, but you don't want to get warnings. And so that way we can kind of modernize, modernize and the language in a way, modernize the code base, I would say, to just follow kind of a canonical modern approach. And so as a user, I want that. I want that to be enforced by the compiler, because that's the only way to really make this work, especially once you have multiple people working on the project. It's hard to, first of all, sometimes it's, everybody's busy. Our job is to, get implement something, get it done. But if part of the requirement is to make sure the code still compiles without warnings, which that's kind of most people agree on that, well, then we can use that to kind of enforce some nice, conventions. So that's another thing. Another thing that I would like the compilers to be doing is to actually generate fast code in all cases. So historically, Fortran compilers were one of the best in terms of generating performing code. But last, maybe 20, 30 years, they started very high, but did not really improve that much compared to the competition. And so C++ and C compilers now pretty much caught up in terms of performance, but there is still a lot of performance left on the table. Typically, so in Fortran, you can operate on arrays as array operations or all kinds of nested loops and so on. And it should not be difficult to optimize some of these things much better than the compilers currently do. To give just one example, let's take a matrix vector multiply. So if you write it just using two loops and just multiply it by hand like that, the Fortran compiler will generate decent code. So would C++ compiler if you do that, and the code would run roughly at the same speed, except that neither of them would get you the peak performance. And historically, matrix vector multiply was very difficult to get the peak performance. You have to do it in assembly. It just gets very complicated. But lately, all modern CPUs have fuse, multiply, add assembly instruction, and they are very good at kind of hiding latency. And so it turns out you can get the peak performance if you unroll the loop correctly and know which of those two loops to unroll exactly and how to do that. It turns out Julia has a nice library called loop vectorization, which does exactly what I just described. You write the loop in Julia, and then you call this library, and then it optimizes the loop to get you pretty much the peak performance, much better than C++ or Fortran compilers would give you by default. So as a user, what I would like is that the compiler to do exactly the same thing that the loop vectorization is doing. And so this is just one example, but you can, there's a lot of examples where the performance is left on the table, and the compiler, just like with SymPy, it's almost the same thing. So with SymPy, I thought, well, why cannot the library do the integrals that we know how to do? I know that we cannot do every integral, and it's very hard to have a general algorithm to do every integral and systematically. But I know for sure that we can encode many special cases to just get down the integrals that we care about. In exactly the same way, as a user, I know these loops. And so matrix, vector, matrix, those are very common loops in the computational codes. And maybe it's not exactly matrix, vector, maybe it's kind of the same structure, but maybe you do something else with the arrays. There's not that many options. And so having those at least optimized to get the peak performance, that's what I want as a user. And it seems to me it's very easy to do. The compiler has the symbolic, you can think of the compiler as SymPy, it just gives you the code in a symbolic form. All you have to do is transform it like SymPy, just transform the symbolic representation of the code to a different representation. And then the kinds of optimizations to get the good performance, you have to unroll the loop, you might need to rearrange a few things, you have to know which loop to unroll. But by analyzing these loops, we can have these optimization passes and so on. And then we have to, work well with LLVM that we use to generate code. But that all can be done. There's nothing, I don't see anything intrinsically why this cannot be done. It just has to be done. And so, so as a user, those are all the things that I realized, we should fix them. And that, this is what I would like. And I think people, once we deliver and once people, play with that, and I think they would like to have the same things as we are trying to implement. So
that example you mentioned regarding the matrix vector multiplication. So it's something like you have a 3x3 matrix and then you multiply it with a 3x1 matrix, right?
Yes.
So that's something which we require on a, like I cannot live half a day without that thing. So we have something called the Cauchy's theorem from elasticity. So it's the traction vector is equal to the stress tensor times the unit outward normal. And the computational representation of it is through a matrix and a vector multiplication. And each and every problem that I do, I have to do that over and over again. I mean, that's the entire representation of the boundary conditions.
The only thing is, if it's 3x3, it's then it's kind of tough because it's too small. But it's then some other ways, perhaps completely unrolling it might be faster. But if you do more like 100 by 100, 128.
Okay.
And those kind of matrices, you, at least for computational stuff, you also need all the time. Most computational codes have some kind of matrices like that. All electronic structure codes have that. Most kind of solvers typically have some kind of a matrix that they need to operate on and so on. So be able to, and it's just a simple example, but yeah, it's one of them. Of course, for matrix
for larger kinds of matrices, you have those stiffness matrices, maybe in finite element codes. So for those kinds of things, definitely you'd need some things like that.
Of course, if it's just a matrix vector, you can just call a library like MK or Open. It has the optimal implementation, but oftentimes you don't do it. It's kind of an example of the kind of loop that you want to write by hand. But it's not exactly matrix vector. Maybe you want to do something else in the body of the loop. But typically you typically have some kind of arrays in the function, and you do some operation on them in the loops, and you return it as an array. It's a very common operation in almost all computational codes. And so be able to optimize at least some of those loops, would go a long way. Like optimize to get the peak performance from the CPU. And the current compilers, neither C++ nor Fortran are able to do that. And so that's kind of very disappointing in a way. It's still very fast, don't get me wrong, but if you can get, twice or 4 times better performance by rearranging the loop, well, that's a big deal, I think. And so as a user, that's what I want. And so, yeah, I can tell you like why I think that is. Now, when I am in the compiler business, I think what happens is that writing a compiler is it's a huge task. And so what most new compilers do, they write a parser, then they have, and that's a lot of work. Turns out, just only getting the language to parse is a lot of work, and then they parse it to abstract syntax tree. Typically, it's called AST, abstract syntax tree, and then they do all the semantics, figuring out the types and so on, and then the runtime library. It's a very kind of a low level work. It's a work you have to do as a compiler, because in order to compile the code, you have to do all these tasks, but it's very intellectually not very stimulating. It's just something you have to do. And then by the time you're done, you're so exhausted that you just kind of are happy to just generate code, so that at least it runs. And so that's kind of how most compilers start. And then lately, well, let's say with GCC, it started a long time ago. I assume that's how they started. And then they added optimization passes. And so they have some kind of intermediate representation that does all the optimizations. But typically, at least historically, that representation is typically low level. In let's say modern times, we have GCC and we have LLVM. Those are the two, I would say, main kind of tools. And both of them, in a way, conceptually, it's not that much different. They each have their own low-level representation. It's kind of like high-level assembly. You can think of it that way. So you still want to do that and optimize on that representation. But the kind of optimization that you can do are things like function inlining. For example, loops are completely unrolled, at that time. I mean, completely flattened, it's just a jump. What LLVM does, as well as GCC, they reconstruct the loops. So the front end takes a beautiful loop and converts it to a jump, just jumps and break, like if and kind of conditional jumps. And then LLVM takes it and tries to reconstruct the loop. So that's, that already tells you something is not, not right. LLVM is amazing. And so is GCC. They are able to reconstruct a lot of loops, but and then once they reconstruct it, then they can unroll it and do some optimizations on that. But it already kind of, probably tells you cannot do every optimization like that. And especially once your code is complicated, multiple nested loops, and as well as high-level Fortran constructs. For example, you do some array operations, or you call some runtime library functions inside the loops, very common, sines, cosines, and, these kind of things, or using, defined functions too. By the time it gets to LLVM, oftentimes it might see, or sometimes you do maybe some allocation on an array or stuff like that. By the time it gets to LLVM, it sees kind of calls to a runtime library. And so it doesn't even know how to optimize it. It's hard to do that. And also, even if it sees all the code, by the time it gets lower to this low-level representation, it's too late to do some of these optimizations that we would like to do. So the whole design, if your compiler only kind of parses the language and does semantics, but then lowers to whether LLVM or in GCC their own representation, you can only do that much. And so when it comes to these loops, you really want to see the original language and really see as the loops as written and optimize those before you lower. And I think historically, just, it's hard to redesign a compiler. Once it's written, it's extremely hard because it's such a big project. And so I think, for one reason or the other, I think most compilers just kind of do the semantics and they just kind of lower. And so with LFortran, what we do is we parse to AST, but instead of doing just the semantics and lowering, we actually kind of, we have a representation called abstract semantic representation, ASR, which it's not lowered. So it represents every Fortran feature faithfully. So in other words, it has for loops, it has all the types, it has every semantic, construct of the language is represented 101 faithfully. So you can, for example, take that and transform it back to Fortran if you want it, and you will not lose any. You get a functional equivalent code, high-level code. And so what that allows us to do is to do optimizations at this high level. And so, for example, we started adding things like, let's say you call a modulo function and you want to flip a sign of, to give an example, when you want to implement a sign function, you want to do argument reduction. And so you typically have a construct there. If the modulo of the argument is, if it's odd or even, then you want to flip a sign of the argument. Let's say for a sign, depending on the quadrant which you are in. It's a very common operation. Well, it's hard to optimize if, if once you lower it, and maybe it's a runtime function call for the modulo and so on, it might be hard. At the ASL level, it's super simple to write the optimizer. So what we've done, we literally kind of pattern match that operation, and we see it, we transform it to our own runtime function, and then in the backend we implement efficient assembly instruction. You can use some bit tricks on how the floating point number is represented to get a very fast implementation. It's just an example. It's very natural to do it that way. And so with the loops, we are planning to do exactly the same thing. When we have the loop structure, we would like to optimize it at this high level before we lower it to LLVM. And that's how I think we can get the performance, the peak performance.
So Ondrej, you have talked quite a bit about the backend of things. So as an end user, so I was pretty excited to learn about the interactivity that you mentioned with LFortran. So how does it actually look like? So as an end user, what do I actually look at? Because I haven't tried out LFortran, sorry. So can you just tell us, like,
it looks like,
for example, in MATLAB or Python, if I just write 2 + 2, it gives me 4, right? And if I write x + y whole squared in SymPy, it gives me x squared + y squared plus and well, dot expand. It'll give me that expansion. So how does it work in Fortran in a compiled language?
Same thing. So so to launch Python in the terminal, you type Python, and you get a prompt. You can do 4 + 4, you get 8.
Yeah.
So with LFortran, you type LFortran in the terminal, you get a prompt. You type 4 + 4, and you get an 8. So it looks exactly the same. Yeah. And then for variables, so it's still Fortran, so you have to declare variables. So if you type x = 5, it tells you that x is not defined. But so you define it. You type integer x that defines x as integer, and then you do x = 5, and now you have the variable, and you can do x + 5, whatever, just like Python. We can even make it even closer by not requiring to declare variables, but it's one of the things that I'm not sure if it's a good design, and so we'll almost definitely have it as an optional using a compiler flag. But I don't want to make it the default, at least not now, because if we make it the default, we can never take it back because people start using it and then it will break their code. So I want to be careful with that. But technically, it's even possible to insert the variable types automatically from the right-hand side. So it can look almost like Python.
Okay, now you are getting me excited about this. So, you remember how in MATLAB, once we run a script, then in the workspace, the variables get stored, right? And I think it's a similar sort of thing in interactive Python also.
Again, if you create a script, the variables get what?
They get stored in the workspace of MATLAB, and then from the command line you can access those variables and play around with that. I used to love that aspect of MATLAB during my PhD work. So I mentioned to you over email, right? My entire PhD work was in MATLAB. So is that something possible in using LFortran also? So you have a separate script, like a proper program, full length program. A .f90 program in Fortran, you run that, and all those variable values, the output values, they get stored in some kind of a workspace, and then you access that from the LFortran prompt, something like that.
Yeah, so I guess we haven't implemented yet to load a script from a file, but we should do that. Now when you are mentioning it, it's a good example. And essentially, I think Python or IPython works the same way.
IPython works the same way. Yeah, you just have to be a little bit careful with the directory, which of course you have to be in MATLAB also.
So in Python, if I remember well, when you load the script, it kind of loads it in your current scope. So all the variables in that script will suddenly become part of your current scope, and you can use it.
Yeah, exactly.
So LFortran works exactly the same way. We just don't have it yet implemented to load the script. But if you copy and paste the script by hand, as the temporary workaround, it will behave just like you described. So every variable now becomes available in that prompt, so you can use it, and it has the value that it has. So you can do some specific computation and store the result in the variable, and then you have it. You can use it interactively.
That's wonderful. I have to try this now. Because I think the way that I used MATLAB, I think it was just as a more forgiving front end for Fortran. I barely even used any of those built-in fabulous functionalities of MATLAB, except maybe OD45.
Yes, that's what I realized too. I think I think it'll be exactly what people want once they see it. The only thing I have to warn, LFortran is in alpha stage. So what that means is that it works interactively, compiles to binaries, but it has limitations. And so you need to be willing to work around the limitations. So you'll discover things that are not implemented yet. So typically you get some kind of an exception saying it's not implemented yet. So that's not going to work. Also in the interactive prompt, the compilation into binaries is pretty advanced. We can compile quite a lot of Fortran. We have modules and subroutines, functions, and almost every Fortran feature is implemented to some extent. But some of the advanced features like classes, they are implemented in the most basic form. But you try to do anything more advanced, it will not work yet. But we have arrays, we have all those integer complex, real types, we can functions, we have C interoperation, we have quite a lot of things, but not everything is implemented fully. And so you'll almost always discover something that doesn't work, but typically it's possible to work around. Now the interactive prompt has even more limitations, so you'll discover bugs. It's in alpha stage, but our goal is to bring it now to a beta stage, which in my definition is that it needs to pretty much just work. It will have bugs, but for the most part, I think pretty much everything should work. So we are not in beta stage yet; we are still in alpha. So it's kind of a caveat. If you try Fortran, report all the bugs you discover.
That's fine. That's fine. Absolutely fine. All right. So there's one contentious point which I had mentioned earlier. So as you can see, so I'm closer to your age, and I got immediately excited by Fortran, even though I have never actually used Fortran for any of my projects. I did touch upon it a little bit, but I never really got around to actually using it. But still, I got excited by this prospect of, like if there is a real full-fledged functionality of involving the interactivity in Fortran, I think I would ditch everything else and just move over there.
I think you're not the only one. I think so. I think I've got to mention. I think once we get to beta,
yeah,
I think huge boom of like once people try it out, realize, oh, this is superior. There'll be a lot of users of this.
Yeah.
I mentioned at the lab where I used to work. Every group had maybe one person who used SymPy maybe once a month.
Mm-hmm.
Once we deliver on LFortran to compile the production codes, there'll be people in every group who you would use it every day. And so that's a whole different game, different.
But here's the contentious point I wanted to raise, that these old timers like us, arguably speaking, so we would definitely get excited, right? And I think you would also get a lot of excited people among the absolutely young generation. So people who would like to actively develop to something so very new and at the same time old. However, for production purposes, let's say we have a senior graduate student or some kind of an early career research person. How do you think they would take to it? Would they start gravitating towards Fortran? What is your take? Like, it's just there's no correct answer here, right? So how do you think would they gravitate towards it? Would they shy away from it? What do you think will happen?
It depends. I think in general, maybe if I can generalize your question, the question could be reformulated as what is the future of Fortran, or what is does it make sense to invest in learning Fortran and using Fortran? And I don't know. So the way I see it around me is that Fortran historically had a lot of production codes, millions and millions. It still has, but in terms of where things are moving, in what I see, at least personally. So the reason I'm saying personally, because other people disagree, but what I see myself in my own eyes and my own experience is that these projects are moving away from Fortran to C++ at an increasing rate. And the reason is that a new supercomputer comes in, has GPUs on every node, you need to be able to run it. Maybe not ideally, but at least you need to be able to run the code on those GPUs. Otherwise, it's hard to justify. Well, partly political, but partly practical reasons. You need to be able to run on it, and it's sometimes completely impossible with Fortran. Sometimes it's possible if you rewrite the code a lot. And with C++, at least you have libraries like Cocos as an example, array libraries that just run on GPUs. Maybe not ideally, maybe have all kinds of limitations. The C++ code, in my opinion, is much more verbose or less readable. If you compare Cocos code, how you actually have to write C++ code, and the array code compared to Fortran is much more, slower to compile, worse error messages, possibly worse performance on the CPU. Almost everything is worse, but it runs. And so that's the number one. You need to be able to run on modern platforms. And so, and it's like, if there was a path forward, I think people would be willing to work around, just like they are willing to work around the C++ limitations. But C++ at least has a path forward. Fortran, in many respects, does not have a path forward, or in the minds of the people who have to run these projects. And so that's kind of the main reason, as I see it. Now, I think this can be fixed. I think one of the reasons I want to also fix it, I don't see why the Fortran language could not run on the GPU kind of naturally and provide the infrastructure and so on in the compiler. But I think that's the main reason. Yeah. So to answer your question, I would say for the big production codes, a lot of the new efforts are in C++, as I can see, for the reasons I mentioned. So then the future is not so bright. But the way I see it is that it's kind of like a huge ship. And so in a way, there are these big codes that are in Fortran, and then there is nothing in between, and then there are some very small codes kind of from that people are starting, and there's nothing in between, and then the tooling is kind of and as well as kind of actually running on these platforms is just not really existent, or not very good, not in a good shape. And so in my mind, what I see is that I'm focusing on these small projects kind of from scratch. Like you mentioned, you would be excited to try using it. There'll be a lot of people like that, I have no doubt. So I think that's kind of what I call it, a resurrection. I published a blog post called Resurrecting Fortran, and a lot of people objected. They say, no, Fortran was not that, this is not called it resurrecting. But in my mind, I thought about it a lot, and maybe, I had a lot of arguments with that, but I still think, the way in my mind, it's just not doing great, but I think we can fix it. And so start for small projects. When I talk to, let's say, postdocs who come, came to Lionel, I asked them, what tools do you use to program? And they say, well, MATLAB, Python. And then I asked them, what do you do to run in production? And they say, yeah, then I rewrite to C++ or Fortran. And I asked them, well, what if you could do everything in Fortran interactively, and then you have it? And they say, oh, I would use it right away. So you see, I think that's what will happen, is that people, start kind of using it for small projects, and we build up the community. We actually are making excellent progress in kind of building up the community around Fortran. And in my mind, I'm focusing kind of on small projects, and kind of laying the foundations, the infrastructure and the foundations. And since we only started 2 years ago, let's say, you cannot expect, to have, to be ready for production for big codes in 2 years. It's just,
Absolutely.
And so if your goal is to work on these big production codes, then it depends. But, if I was a manager of a big production code, maybe I would move to C++ also, because you need to be able to run, in the near time frame on these machines. And so, and also the tooling, you don't have to fight the tooling and so on. But anyway, so that would be the answer. So if, to you, as you were saying, as you were asking about somebody who's finishing the PhD, let's say, it depends on what kind of code they are thinking of contributing. If it's their own code, I did, my PhD in Fortran, and I would do it again. But if it's some kind of a bigger production code, then ultimately it's not even their choice. Typically, you have to use the language that the code is written in, and that's increasingly, I would say, C++. But I think once we fix the infrastructure of Fortran so that we can, for small projects, and we kind of build up the community, I think things can change. So in the, if you ask me in 5 years, things can be I'm hoping very much better.
So one encouraging thing that I have actually noticed, so this is my own experience as a layman user, is that during my own PhD days, when I was using MATLAB day in and day out, in one of those days, one of those weeks when I had more time and not much money, and you just faff around on the internet, I was maybe tinkering with the idea that maybe I could start using Fortran because, as young graduate students, you always gravitate to the entire philosophy of open source and the traction of it. It was really hard to get any information on Fortran. It was really, really hard. I couldn't make head or tail out of it. Like, should I start writing a program using .f77 or .f90? What am I supposed to do as a beginner? So I was scratching my head literally. But now after I decided that I would have this discussion session with you, I looked up the things that you guys have set up. It's beautifully structured, beautifully organized. I wish I was younger now. I really wish I was younger.
Thank you. That I'm happy you're saying that. That means people who are younger, I'm hoping they will contribute. They are. I think that's how things will get resurrected. And I think I was in the same position about 10 years ago. I wanted to kind of see what is the state, like how am I supposed to program in Fortran? And just like you, there was nothing. So I actually created a page, fortran90.org, back then 10 years ago, and I just kind of painfully figured out which way you are supposed to use Fortran and documented it.
By the way, I'll put all the links in the description of this video, all the great websites that you guys have created.
Fortran 10 years ago, but I was hoping to kind of create a community around it, but failed. It's very hard to, as anybody who tries, very hard to create an open source community. But we succeeded with Fortran Lang, and we are in the process. We already ported the tutorial, and we are in the process of porting the Fortran 90 page completely to Fortran Lang. So it's just one resource, one page, one Fortran page. The Fortran Lang, it's one in a lifetime opportunity. We managed to pull off something that I would not think is possible. If you searched Fortran in Google, let's say 2 years ago, there's nothing. There is you just get random pages. There is you just get kind of random pages. There is no central page.
Yeah.
No authoritative source of, and no centralized community. The community, in a way, that I would say turns out there's a lot of people who still use Fortran, but yeah, they are not organized. And then, and also no logo, nothing. Well, and we managed within a year, I think we managed to create a page. And when you search Fortran, it's now the second or first page in Google and every other search engine. The competing page is Wikipedia for Fortran. So, some search engines put our page first, some page put it second, but either way, if you just search Fortran now, our page, the fortran9.org comes first, and it's open. The page itself is open source. I'm encouraging anybody to contribute. We run it as a community maintained resource. We have a discussion forum. Anything you would like to change or improve, let us know. You can, and we also are looking always for more contributors. But the fact that we managed to create a page for Fortran, that you now search Fortran and the page comes up, it's amazing. I thought it's not possible. And then the other thing, we actually created a logo for Fortran. Also, I thought it's not possible. We created a logo, and then somebody put it on Wikipedia, not us, and elsewhere. And now it's I see people when they let's say compare languages, they use the Fortran logo that we created as a logo for Fortran. So again, it's just something I thought it's not possible. And so I think that kind of brings me the hope that I think we will succeed ultimately. And so we bootstrap this community, and that's doing really well. And I encourage anybody who wants to learn anything about Fortran to join and ask questions and so on. My own focus is mainly on the compiler, because that's something where it still needs to happen. You can have all the community you want, but you need a good compiler. community kind of controlled, maintained compiler that we can implement what's needed. And so that's long story short, yes, I spent a lot of time bootstrapping, and I will join with many others, Milan and Lawrence and Sebastian and many other people, Vipul and Peter Klosler and others. We really managed to bootstrap it, and so I kind of am not, I don't want to say stepping back, but I'm focusing 100% on the compiler, because that's the last part. It absolutely has to be delivered. Once we do, I think things will start looking bright.
Yeah, all the best for that. Okay, so for someone, let's take a step back now. So you have spent formally the bulk of your career being a computational scientist, right? So these are like labors of love, SymPy, Fortran, but your day job has always been as a computational scientist. So for similar kind of people, and for the younger students, when I say computational scientist, I don't mean a computer scientist, right? So people who use computational work for stuff in physical sciences like physics, chemistry, biology, mathematics, applied mathematics especially. So that kind of stuff. That's what I mean by computational sciences. So for somebody who is starting out his or her career as a computational scientist now in 2022, what would be your advice for the choice of a programming language? So I have been guilty of peddling expertise where I have actually none, and advising younger students to stick to a particular language, to learn the syntax of that language, and to spend more time thinking about the heart and soul of programming itself, not tied into a particular language. So this has been my advice generally, that maybe just stick to Python, but learn the spirit of programming first. And then as you grow up, you can pick up other languages as you go along. You won't find it difficult. But I think an advice from you would be better, because I'm not really qualified for that kind of advice.
No, my advice is exactly the same. Learn Python, stick to Python. You have to know Python, because when I started with Python, it wasn't the most popular. Now it is the most popular language.
Right.
I mean, many depends how you measure it, but one of the most popular. Let's put it that way. Python, I would say for computational science, I think scientific computing, maybe different term. Python is the king. You have to know it. So I would start with that. And then if you have cycles for more, learn some compiled language. C++ is good to know, and Fortran is good to know too, I think. Those are, even if you will not use Fortran, it's good to know at least. It's been the first high-level language. It's good to know, if anything, then for historical reasons. But I think once we resurrect it, I think you will like to learn it. I'm hoping you will like to learn it, but and also learn C++, because it's just a very good tool, and so I recommend that. But definitely start with Python and stick to Python. Just do everything in Python. Learn the libraries, get things done in Python. And then as you need speed, you can either try some of the Python compilers, or just write it in C++ or Fortran.
So is it perhaps possible for the growing Fortran community, that you're one of the prime drivers behind it, to maybe get in touch with the academic departments and the universities to, I wouldn't say push it, but something along that line. So if we have young takers, because a person learning a compiled language, or maybe even students who are familiar with MATLAB, I don't think they would find taking to Fortran too much difficult. And maybe over the next 5-10 years, that can pay dividends, and not just in dividends in getting more political supporters for the Fortran movement, but actually people who can contribute fruitfully to the progress of computational science using these tools.
Yeah, well, I think one thing about Fortran is that the next question that will come is, well, can it run? How do I run it on the GPUs? And then the answer, and then once you start hearing the current answers, you'll, in my opinion, people will think, well, that's ridiculous. I mean, I'm not going to be using one commercial compiler to run on the GPU and another commercial to use on AMD and then rewriting the code or just writing it in C++ and calling from Fortran, just so that I can run on the GPU. That's just ridiculous. Those are just, to me, unacceptable answers. And so I think Fortran has to have an acceptable answer first before trying to, I think, kind of going to academic departments and pushing it there. I think, so for example, let's say what I would like as a user, and an answer that I would take that is a very solid answer, is that you write your code in Fortran, and then maybe you need to annotate some of the arrays that they are on the device, let's say, and then you compile it through a compiler, and it is going to run on AMD GPU, and it is going to run on NVIDIA GPU, and you will not be getting pretty much any, or it will run on the Windows and interoperate with MSVC, the Visual Studio C++ compiler on Windows, which, by the way, GFortran is the most. So I'll get to the current state, but the vision is it needs to run on a Mac, on Linux, on any HPC cluster, and so on. And until we get there, I think it's kind of I don't want to be pushing it too much. I rather want people to discover us, and like you did, and realize, oh, this is exciting. I want to try it out. That's the audience I'm targeting personally right now. I don't want to go to a CS department and say, or engineering department and saying, oh, why don't you teach Fortran? Because I don't have the answer. I don't have an answer that I like to these questions. And so we will have the answer. Once we run, I think universities will and professors will love it. I mean, why not? It will be cool. But right now, so the current state is the best open source compiler is GFortran. It's a great compiler. It's a lot of people, a lot of people who contributed to it. They've done it's a lot of work, and it's amazing that they managed to really it can compile any Fortran. It works and so on. But for example, on Windows, it cannot, because it's part of the GCC, it cannot link with MSVC. So if you are, a lot of people are using Windows and they are using MSVC, and they need to be able to interoperate. They need to be able to link C++ code, compile with MSVC with Fortran code. And with GFortran or GCC in general, it's very hard because it uses a different object file and so on. It's a technical problem, but it needs to be solved. And then, of course, the GFortran is a great compiler, but it doesn't, out of the box, doesn't run on GPUs. It has, you can use OpenMP, I think, offloading, but it's just not there yet. I would hesitate to kind of, bring it to a engineering department as a production ready tool to run on GPUs, and recommending them to use it as kind of production end users. You see what I mean? Because then if it breaks, and it will not, and there will be all kinds of issues, that's just not a good view, if you see what I mean. And so, but in terms of, CS departments, I think when I started, I'll tell you a story to kind of give you an idea that that's absolutely possible, and I think they will love it. When I started LFortran, I didn't know anything about compilers. So I designed it the best I could, what I read, and I read compiler books. The most famous book is the Dragon book. It's a very thick book, but you quickly realize when you read it, it's not very applicable to what I want to do, because they spend half of it on parsing. But parsing, you have to parse, obviously, but so I ended up using Bison and RE2C for the tokenizer because it's very fast. Speed of compilation is important, but you get it done. And then the other half of the book is spent on the backend, how to implement the backend. But in modern times, you can use LLVM if you care about performance and so on. It's great. But what I care about is the actual design of the compiler. And so there's only about 50 pages of the whole thick book, kind of with that aspect. And I was not very impressed by that part. And because, it's tough. So I designed it a certain way. And then I went to the Czech Republic. I think I was visiting, and then I had some contacts at the university, the CS department. And so I go there, and so I set up with the professor, I set up a meeting, and I was like, oh, it's going to be embarrassing. He'll kick me out of there like a crank. So I go there, and I, the design of the compiler, showed him what and he was like, it's not too bad. That's what he said.
Congratulations.
So he got it, I got it approved. And And then, and the next question, he says, why Fortran? And so I explained, the motivation is interesting, and so he did not kick me out of there. And then the next year I was much more advanced and I came there again and we spent actually maybe 1 or 2 hours actually discussing all the details. And he was very interested, and I think the CS departments for sure will be interested in this because they like compilers. And it's, we'll say they like compilers a lot. And so there's a lot of that in Fortran, in LFortran, let's say. And then for engineering and other departments, it just needs to be usable like Python is. You download Python and you download these libraries and use Conda or Spec or whatever way you want to install it, pip, and it will work mostly. So, or it can be made to work. So if it doesn't work, typically it's possible to make it to work. But, and it will run and you can use, and you have libraries to run on GPUs and so on, and it will just work. And so we need to get to the same stage with Fortran. So yeah.
Yeah, I think usability is great. So so just going back for just a second on the SymPy thing. Currently in SymPy, you cannot state that there are two positive variables like A and B, and you cannot say that A is less than B and then expect all the computations to properly replace all the places where A has to be less than B and then get replaced. So we have to do that manually. So this is particularly important for problems involving beam bending, where the load is placed at a certain point, and you know for a fact that that distance is less than the entire length of the beam, but still, I mean, SymPy, it's hard to make SymPy understand automatically. So I mean, at the very last, we do the entire work, and then in the last step, we just do a manual replace, and it works perfectly. There's no problem. And I told the students to do this, and they have taken it. So no grudges, no reluctance, nothing. If it's usable, it works with one extra line of, I mean, it's a little annoyance we can get over. It's fine.
And so as long as you're willing to work around the current limitations, Fortran is perfectly fine for production. Has great compilers, and then if it cannot run well on the GPU, then you just don't run on the GPU. As long as you can take that as an answer. Yeah, if it doesn't, then don't use GPUs. Like, it's much easier to not use them in terms of programming anyway. So if that's, then I would say Fortran is perfectly ready. It has been for 60 years. It's been so but as I said, you must be willing to work around these limitations. And so for some applications, it's not what you have to run on the GPU, as an example. So then you are really in big trouble. But as long as it's like students, myself included 10 years ago, it works beautifully, and you get beautiful performance, very readable code. It's easy to program in. You get good error messages, quick compile times. You get a beautiful binary. You optimize it. So first of all, in debug mode, you enable bounce checking. So I don't know, your viewers might not know. Fortran code in debug mode, if you enable all the debug mode flags in GFortran, cannot seg fault. There can be some bugs in a compiler, but assuming there are no bugs in the compiler, the code pretty much cannot seg fault, and it cannot leak memory as long as you use allocatable arrays. So keep that in mind. That's amazing. And then you enable in release mode, you enable all the optimizations. It can seg fault in release mode because you don't do bounce checking. You don't want to do bounce checking. But the idea is that you debug your code in debug mode and run the test suite and run your even production kind of input file, at least a few iterations to kind of see that everything works. And then you recompile in the release mode and you get beautiful performance, very, very hard to match from C++. It always is possible to match, but a bit more work. Even myself, when I do some kind of computational task, it's easy to do it in Fortran. I get decent performance, and then I rewrite to C++ and I get slower performance. And then I spend hours trying to figure out why. And I can always match it, but it takes more work. And so, if that's I think Fortran is awesome from this perspective and completely ready for production. But as I said, it has these caveats, and if you're willing to work around them, then it's perfect.
So Ondrej, sorry, I'm overshooting the time. Is it okay if we just keep the discussion going? I really want to ask you a few more questions. All right. I have all the time in the world. Nobody's going to disturb me now at 11:30 at night. Okay. So the role of research software engineers. So, this is something I think which even though you were not tagged formally as one, but I think in one sense or the other, you were something on that line, right? A research software engineer. I mean, a computational physicist on one hand, but also a research software engineer because of the very nature of the work that you're doing, very, very fundamental level. But there are proper research software engineers, not many of their breed, but I think it's a growing breed. So what kind of role do you envisage for them in the academic world, in the industrial world? It's always dangerous to make predictions, especially if it is about the future. Some wise man said that.
So can you define what a research software engineer is?
So these are the people who would be part of a larger scientific project, but their main job would be to develop the codes which would be much, much better written than a professor or an inexperienced hand at coding would be.
So maintaining.
They would respect some of the more traditional production quality standards of software development, but in a research setting.
I see. Yeah. I guess that was the group I was working on at LAL. Was most of our tasks were, or a lot of the people in the group were maintaining the large physics codes and implementing new methods and like numerical methods, even doing basic research. But most of the, or like main, I would say, focus was on developing new methods and maintaining and speeding up the current methods, as well as making sure the codes run on modern hardware and get good performance and so on. So if that's the task of our research, yeah, I mean, so your question is what I see as a future of this branch? Yeah, I mean, I think you always need
I was thinking more along the lines of, so suppose there's some guy who, because of some experiences that he has grown up with during his undergraduate and masters, he joins a research group where his main utility to the research group is along that line as a research software engineer, and he spends maybe 4 years, 5 years in that group, publishes papers along that line because he has been contributing to the code. But then he graduates one day, and then maybe he gets a great job as a postdoc also, because that kind of skill is really, really highly required. But when it comes to an academic position, if the only strength he has to show is on the numerical side, or maybe on the software development side of things, and to every question that what was the scientific initiative that you took, for that he has to pass the buck to his line manager or to some collaborator that he has worked with, and never something that he has started on his own. I know it's a contentious question, but do you think that would be a wise decision?
I see. Okay, so I guess it's a question about the career.
Exactly.
Well, then I would say you just have to decide what you want in a career. Like, what do you want to do? So, and then you go from there. So in my case, I wanted to, after finishing a PhD, I wanted to work in. I wanted to do some basic research as well as computational physics, and work with people who do that and really learn a lot and publish, and also. So I was looking at positions like these, and of course, I did, as I mentioned before, I really enjoyed working at the lab. I used to work at Livermore too. I think I worked there for about 8 months, and great people there. I think all the national labs in the US are awesome from this perspective. And I collaborated with people from LBL, Lawrence Berkeley Lab, and Sandia and Oak Ridge. It's just great, great environment, and I really enjoyed that kind of environment. And so if let's say you would like to get into an environment like that, well then you apply for, well, there's multiple ways to get in. I went through the postdoc route. So you apply for postdocs. So to get accepted, so let's say the question is, how do you get accepted as a postdoc? So you have to, I think people are looking for the skills that you have, some publications. So that comes back to during your PhD, publish something, show that you know how to program. It's good to maybe have some projects. I think either your own, or I think it's fine if you contribute to other projects, as long as you can show what the contribution was, if you implemented some new method, or maybe sped up the code, or maybe ported the code, or whatever maintenance you were doing, if you can show what it is, and then I think that's great. And then once you get in as a postdoc, then it's much easier to get a job as staff. That's the route I took. Because once you get in, I can give you the advice right away. Once you get in as a postdoc to any lab and so on, make a lot of friends, a lot of colleagues, like a lot of get to know a lot of people, see what they work on, and then as you get connected, use the 2 years to kind of get well connected, and then typically you can find either opening or some ways to get in. So that's the route I took.
Yeah. Okay. So I mentioned just before we actually started this video recording about that little incident with Professor Neil Ferguson's COVID SIM code. We are not fully out of the pandemic yet, so it's probably relevant that we talk about it. So for people who don't know, a lot of the policy that was done in the UK was, I think at least, I won't say a lot, but a part of the policy making was done based on discussions with his team, Professor Neil Ferguson's team, and based on the research that they had done. And they actually ended up making the code, the COVID SIM code, public. And when it was made public, proper professional software engineers, I mean, they had very, very negative things to say, to put it mildly, about that code, saying that it was a mess and whatnot. And there was a lot of back and forth, and more trained people who had seen both the sides of academic research and the professional practices. They gave a more nuanced thing. So as I was mentioning, Dr. Konrad Hinsen from France, he gave a very nuanced argument both for and above the various nuances of it. And so what is your take about these things? So people who are developing these kinds of codes from scratch on a blank file, and then over years and years, maybe 5, 10, 15 years, some big code develops, and then it is, for want of a better word, a mess, which would not actually happen in a real professional software engineering team. Do you see any way out for this? Maybe there's a bigger role for research software engineers, as we were just discussing earlier.
Yeah, I mean, I've seen a lot of codes, but I don't claim that I know how to develop anything like that. But my own view on this is that, first of all, I've seen large teams developing terrible codes also. So it's not just the fact that you have a team of very good people. It doesn't mean that you deliver usable code. And the reason is that once the code becomes big, it's actually it requires quite a lot of, I would say, experience designing it, so that, and ensuring that as people, especially if you have a larger team of people contributing to it, that it doesn't become a mess. Because I think my experience, at least, is that almost by default you can assume that any big code becomes a mess. So, for example, with the LFortran compiler, it's a compiler is a huge task, and so that's why every compiler is a mess, simply because it's a big code and a lot of people contribute to it. And oftentimes what happens is that people contribute a little fix and they don't have the time to understand the code and so on. They just want to fix some particular thing and they do their best, but it's for others to maintain the fix. And so, so that's for compilers. Now the scientific codes, so it depends who develops it, but oftentimes it's the same thing. So let's say a student wants to implement some new method or some new feature, but they do, and they do their best, and then they leave, and so somebody else has to maintain it. And so it depends on who is in charge of the code and to keep making it maintainable. Now, coming to the COVID code, I forgot exactly if it was just a single person code.
Sorry, say that again.
A single person write the code mostly? No.
So it was his entire team. I think they had developed the code over many iterations, and they had applied that same code. So this code was basically a translation of the actual research work on the COVID model. So he's a mathematical biologist, Professor Neil Ferguson.
Developed by a professor and his students?
Yes, exactly.
Yeah, I've seen a lot of codes like that, and so I'm not going to comment on this particular code because I don't remember the details, but what I've seen with other codes developed like that. So you have a typical, let's say, a professor at a university and his students. So the students help with the code and contribute new methods and new research and so on. The professor typically doesn't even have time to really work on it, even though he would like, but no time. And so this is the students working on it. And he, at best, maybe kind of manages the design a little bit, but, you just kind of patch it up, and then the student develops it for, let's say, 2-3 years, then they graduate, leave, next student comes, different skills, different styles. So it just becomes a patchwork of things. It's just inevitable. It's just the way it works. And so I guess the question is, or maybe your question is there a better way to do it?
Yeah, so can we perhaps incorporate some kind of formal training as part of, like you wouldn't want a student to write an FEM code without first actually formally learning the FEM algorithms. So why not? Why not in terms of the practice of writing code also?
So I think, well, what I'm trying to say, I guess, is that I've seen many codes like that, and they all kind of look the same, and for the reasons I described. But I've also seen other codes. I guess if the person who made, let's say the professor, if they don't let the design out of their hands, and so to say, kind of keep, I guess, reviewing the pull requests and making sure that the design is good, and that they have good test suite and a good kind of engineering practices for the code, I would say. They have a continuous integration, solid test suite that they spend good time.
So Ondrej, I have to interject here a little bit. You mentioned something like a pull request. I would be very surprised if a majority of the mechanical engineering professors or chemical engineering professors or civil engineering professors would be even familiar with a thing like version control. So
yeah. Okay. So I guess what I'm trying, so I'll explain it. But so historically, let's say, when I did my PhD so my professor was a physicist, and a lot of the physicists, and in the 80s there was no, like they did their best, back then the computers were a lot slower, and also these kind of modern development practices were not as known even, or like people were just figuring out how to maintain these, how to develop and how to maintain these things. And scientific computing is also a little bit of a special branch of these things, because we care about performance and accuracy and these kind of things. And I would say it's really amazing that if you look at some of the older codes, that they even work. And not only they work, they are accurate and fast, and they have bugs, but maybe it's really messy inside, but they deliver on the things that truly matter, which is the performance and the accuracy, and get the job done, and implement very complicated numerical methods and physics methods and so on. And so it's and so you cannot do everything, I guess. And so if you are good at physics and good at understanding the methods and are actually able to program them and actually deliver, that can be all that you can do. But I think the modern approach to developing these codes, in my opinion, is to have some of the modern engineering practices. And if you use them, and I'll describe what they are, I think it helps really keeping the code much more manageable. And so what they are, I think, is to use some kind of a platform like GitHub or GitLab or Bitbucket that host your code in a version control system. And again, 20 years ago, there were like 5 of them. Now it's just one. It's called Git. And it keeps every commit, every time you develop a new feature, you develop it in a set of commits. Each commit, you can think of it as a patch, just a change to the source code. It's a series of commits. You submit it to that, let's say, GitHub as a pull request. So the way it looks like, it's kind of like a proposed change, and then somebody else can go in and review your changes, either individual commits or a whole. And then and then of course it should run a test suite automatically, so that the professor is busy. All he has to do is come in and see the pull request change and see that the test suite runs. And he reviews that no changes were made to the test suite, and then they review the changes, and then he clicks one green button and then merges the change to master or main. I guess a lot of people call it main now. So one main branch, and there you go. So, and we can talk more about the workflow. You can look it up online. It's called pull request based workflow. Continuous integration means that the test runs automatically, that your test suite runs automatically online. And so that's part of it. That's kind of the technical part. and social part. And also when you review the pull request, you comment on the individual changes. And once you get into this kind of workflow, that already prevents all kinds of, it improves the code, because first of all, when you submit the code and you actually see the change that you're proposing, you yourself don't want to write too messy code because it looks messy. And, as a professional, you like to submit your job in a clean and nice way. You don't have to be embarrassed about it. And so, certain level. And so this encourages that kind of feelings. And so, as opposed to if you just...
Thanks for pointing that out, actually. So I've been maintaining a GitHub code since, a few GitHub repos, most of which are private because I'm too embarrassed to make them public. But I have noticed this thing that you just mentioned, that even for those private repositories, I don't want to embarrass my future self. So I take care a little bit more than I used to. And for my coursework, for the few repos that are public, the students use them. I certainly take a lot of care. And I think it's a wonderful way, this version control thing. I didn't know it like 5 years ago, but I'm getting familiar with it. But I think there's more do it on the social side of things. So the people, the professors, I think, and I'm not talking about computer science professors, so professors in the physical sciences. So if they start getting to see the benefits of actual version control and things like GitHub, probably they will try to enforce it in their own groups, and that will bring about a sea change in how things are done. So is it perhaps possible to make a layman's introduction to GitHub, like the kind of Fortran pages that you have started generating? Like, I love those pages of Fortran. I mean, I'm so very impressed. So absolutely targeted at layman users like me. So if we can have something which is along those lines for better software practices, software engineering practices, targeted at research scientists, I think it'll be a wonderful step forward. And I don't know if it already exists in some form.
I think there are some. I think this is a known problem. I think Konrad Hinsen, doesn't he describe these kind of workflows on his blog post, on his blog?
Yeah.
I think there are a lot of resources for this. It's as I mentioned, I think the hardest thing is that if you are a professor at university, your main, especially in modern age, your main time is spent chasing grants and writing grants and then all kinds of busy work. So you don't really have time for this, and so it's kind of tough to...
There's always a million fires to put out every day.
That's right. And so it's I'm not, I guess, and I think I can't remember what Konrad Hinsen wrote about that code that you mentioned, the COVID code, but it's easy to complain how messy it is, but you could have written a better code, and at least he has a code that, maybe
exactly. He has a code at least.
It's not the best, but at least there is a code. So but I think in general, yes, I think what I think helps is if it's open source, because that just automatically puts you in the spotlight, and you don't want to put the messy code. Nobody wants. Yep. And so that automatically just brings the code quality up. The pull request reviews, having a good test suite, those are the basic things, and continuous integration. And just having these things helps. And also, what also helps is to package your code as a library or application in some kind of either Conda or Spec or even pip, essentially some package manager, because that puts you in a... essentially you have to look at your code from the perspective of a user who actually has to install it, and you realize, our build system is fragile and this doesn't work and that doesn't work. But if you do all these things, that automatically brings your code up, big time. So I think that's the solution.
I think there's a minority of professors out there in the modern age, so closer to my age, probably a little bit senior, who are doing their quite a bit of work on this, and there's a journal of open source software, and I think Professor Lorna Barba, she's doing an incredible work in this regard. So just like we have scientific papers, so also we have scientific papers surrounding the development of the code, and this is all open source software. So it's not huge, but it is growing, I think.
I haven't actually published there, but I know about the journal.
Yeah. Okay. So, all right. So now we come to the most important question. What is your work setup like? What operating system you use? Which editor you use? Do you have any special workflow which helps in your productivity? Sorry, that was
Right.
just a lighthearted moment.
Yeah, no, it's a good question. I used to use Linux for the last maybe 20 years, but lately I don't know, I use a Mac because I like the M1, the Apple M1 Macs. They're really fast. The CPU is really fast. And so to give you an example, I had the latest Intel desktop machine at Lano, and it was a lot of money and so on, and very latest, and it compiled LFortran in maybe 16 seconds. And then my wife's, we bought this cheapest, for $1,300, this Apple M1, and it compiled LFortran at the same time. So how's that even possible? So this is just, you have to see it to believe it. But yeah, I timed it side by side. Even I clicked enter on both. I log into my computer at work, and then on the local terminal, I hit enter at both, and I finished. So anyway, and then so right now I have the Apple M1 Mac that's even faster. So it compiles it in about 11 seconds or 12 seconds. So anyway, so I just like the speed so much. And ultimately, and regarding the rest, I'm actually, even with Ubuntu, I was using Ubuntu, and I guess I was not really, one thing I learned is that if you start customizing the desktop too much, then you come to a new computer, you have to recustomize everything else. So I just kind of use the stock Ubuntu, no customizations. I use a terminal for most of my work, and I have my dot init, the dot files, with the configuration. But for the same reasons, I try to keep it very simple. So I use Vim as my editor, or NeoVim, I guess, and Git. So I have a Git config file, but that's it. I think those are the two main config files. Lately, I started also to use VS Code, which is an editor, IDE, I guess. But so I use Vim and VS Code, and so on the Mac I still use Vim and VS Code and a terminal, and I don't use anything else. So for me, the workflow just doesn't change. And if I use Windows, I would do the same thing. I would use VS Code. I would use a terminal. I think Windows has this nice new terminal, so I would use that, and I would use Vim also. So I can use any operating system, I guess.
Okay, good to know. So I was using Vim and a bunch of open source software on Windows. And every time I had to tinker with it a little bit, I had to look up online, and all the help was from the Linux guys. So actually I was putting in more effort in Windows trying to get them to work. So I thought that what the heck, let me just move over to Linux. It'll be easier maintaining them. And I have been doing it. So this particular recording is being, I'm on Ubuntu 20.04. So
yeah, there you go.
All right. So from your very early days, you have been heavily involved with free and open source software, except this recent use of Apple M1. So do you have any message to the student community who are similarly involved in free and open source software?
Yeah, just find an open source project that you like and contribute. It, I guess, like on the broader scope, let's say doing SymPy, even though I did not find funding directly for it, it has in a way opened the door for me for all of my jobs. It helped me get to the PhD because so the way I got to the US is that I started SymPy, and then one of the contributors, I realized he's from the Czech Republic where I was. So I met him, and then he met this professor at some conference, and he told me, hey, you should email him. And that's how I got to the US to do my PhD. To do a postdoc, I guess, through SymPy, I meet a lot of people, or they hear of me or get to know me. And so it just opens the doors. And that's the most important thing to progress your career, to get the jobs that you like. And so contributing to open source can help with that, because you get to know a lot of people, and your work, because it's open source, you can put it on your CV, and if you are interviewing somewhere, they can look up what you did exactly. And you almost don't need anything else. If you have good open source work behind you, whether your own project or you contribute to some other projects, list it on your CV. And it, like when I, let's say, interview people, whether for postdocs or students, and if I want to know, what their skills are, if I can see their open source contributions, I don't need to know anything else, because I can see the discussions. We talked about pull requests, so that's the communication is a big part of it. So I can see the discussions, the communication, everything is there. And so it's just kind of it's just a great way to, if you don't have many connections, it's just a great way to get those connections and improve your CV.
And correct me if I'm wrong, since you mentioned CV, I have been telling a few of my students that, look, if you keep on using Windows and stuff around Windows, that's not something that you can actually brag about in your CV, because nobody cares. You're supposed to know that anyway. But suppose you start using Linux and some of the open source software, and maybe you tinker around with a little bit, then that's something you can actually put on your CV, you can brag about. It carries a little bit of weight, maybe not like a published paper, but it's something better than just using Windows. So in a very materialistic sense also, it's probably using free and open source software, it pays in these kinds of softwares.
Yeah, I guess you're right. As I mentioned, I've used Linux for 20 years, so for me that's kind of normal. This is the default, I guess. But you're right that I guess it's if you don't use Linux, at least learn how to use it a little bit. It's a Linux. It's kind of like Fortran. Linux or Unix in general has been around for 40. I can't remember, since 70s, I guess. So a long time. And what's interesting about it is that it's still here today. Even the Mac is based on Unix, based on one of the BSD, I can't remember which one, which is from Unix. And so the philosophy of Unix, which is just have a kind of program for one task and have the system structured around the terminal, and it's a I would say time proven methodology that works. And so if you don't use Linux, definitely learn it at least a little bit. So that you know how to use it.
Yeah, so I had a little bit of experience with Linux as an undergraduate student, just a very, very little bit. I use it much more nowadays. And back then, so maybe 10 years, 15 years ago, it was not as user-friendly as it is now. And it keeps on becoming more and more user-friendly. So, and we were behind a proxy in our campus. So to get the Ethernet working, you had to use something, I think it was called the Samba protocol or something like that. I learned that by fiddling around with it. Then one of my seniors came back from his postdoc with his Apple, with his Mac, and he just couldn't get it to work behind the proxy. So he asked me to take a look, and I had never touched a MacBook before. That was my only time I actually touched one. And I saw that was the problem he was not using. So I just typed in SMB and something and just started working.
Yeah, it's there you go. Yeah, it just it teaches you that the operating system is not a black box, but it's composed of these little programs. And so on Linux, you have source code of all of it, and so it's very nice to just learn. Especially if you have the time, you can dig into all those codes. You can read the source codes. I did. Yeah, I guess I've done all this at high school. It's a long time ago. I haven't really done it too much since. But yes, I recompiled the kernel and I read the source code and bash. I wanted to know how that works, and I wanted to know the init scripts. I wanted to know how the system boots. So you can look up in the kernel exactly the first line, the assembly line gets executed by the BIOS. So you can see, oh, this is how it starts, the 32-bit, mode, and it switches to 64-bit, stuff like that. So it's all there, and then the kernel is finished, and then it launches the first user space program, so you can learn again how it all works. It's nice, it's good to know, and there is not more to it. That's all there is to it. And so knowing, how this all works, it helps. I think it's just really interesting. But
yeah,
just think of it. On Windows, you cannot see because you don't have the source code. So.
Well, you don't have many things in Windows. All right. So so I'd like to ask something on a more personal note. What kind of books do you read? So So
but
technical, non-technical, fiction, non-fiction. So give it a go.
I would like to. I used to read a lot, but I don't have the time because I have 3 young kids, and so besides my work and some open source here and there, I don't have the time for anything else. That I haven't read books in. I guess I read a lot of books at high school and before that, but at university I had to focus, obviously, the school, and after that it's always something. So I don't read too much. Let me ask you, what do you read?
Well, I read religiously one author who is he's Dr. Amitav Ghosh. He's an Indian author, but he writes in English. Absolutely gorgeously beautiful English. So I like his stories. He's a fiction writer, but he's also heavily invested in writing stories around climate change. So building stories around that, I really like that. I sometimes read some non-fiction. So I was reading this biography of Humboldt, the German scientist. So the invention of nature. I think it was by Andrea Wolf. It won a bunch of awards, but it's a beautifully written book. And some books around history, maybe sometimes philosophy, but then I feel sleepy and I close the book. But I don't find so much time, honestly speaking. It's hard. Okay, so final question. I mentioned this in the earlier part of our discussion that that languages, the natural languages that we speak as human beings, it affects our thoughts. And there's a lot of research going on in that aspect. There's even a movie made about it, Arrival. So these aliens come and they and these scientists, they try to communicate with it, and in the process of trying to communicate, they learn the language. This lady, this scientist, she learns the language, and the language itself is such that it allows or maybe it unlocks that I mean, it's a science fiction, okay? So it unlocks that power in her brain to see the future. So it's an exaggerated version of what is going on, but there is maybe some truth to it. So in a similar vein, do you think that programming languages could unlock different abstractions in our brain or different aspects of our brain to problem solve in different ways?
Yeah, I would say no doubt. I would say for sure. To give one example of this is that, say, for the scientific computing, let's say, where I spend a lot of time. Arrays. So if you use a language that doesn't have arrays, say, I've done a lot of I've written, during high school, written a lot of code in Pascal. It doesn't have arrays. It has 1D arrays, but not multi-dimensional arrays. And so without the arrays, it's if you've never heard of them or never used them, then you don't even know you are missing them. And so you just kind of do what you can. And then you learn a language like Python and NumPy. And even then, it's like, because I wasn't used to thinking in terms of arrays. So NumPy allows you to do arrays, but I never used it, kind of never quite understood why would I use multidimensional arrays. And then I learned Fortran, and that's kind of the basic ingredient there of the language, and that's what you use for everything. And then you realize, I can use it to structure. I can structure my algorithms to operate, and I can store the data in multidimensional arrays, and I can use the indices. So for those of you who don't use arrays, I can explain it very simply. You have the array, and you don't think of it as you have a 5D array. So you don't try to imagine a 5D array. You just use these indices to the array to store information. So for example, let's say you do some finite element method, and so you have quadrature in 3D. So you use first, and let's say it's Cartesian product, just to make it simple.
Yeah.
So you have 3 indices as quadrature in X, Y, and Z. And let's say you have multiple solutions. Well, you have an element typically. So you do 4th index element. And let's say you have multiple solutions, multiple orbitals or whatever. So that's the 5th element. So there you go. So you have a 5D array, and you store every index. So once you kind of start thinking in those terms, you suddenly realize, almost every algorithm can be written in that approach. And it turns out that it's also the compilers are very good at optimizing that kind of code. And so and so that's a part of the language. And so I think it's just one example that if you have it and you learn how to use it, it just opens up, it just completely changes how you think about writing algorithms. So after learning that, Now, when I write algorithms, I always figure out what data I have, how to store it. I have to figure out the order of the indices. It matters how it's in, depends on how you access the array. So it depends on the algorithm. You want to access the array in Fortran, always the leftmost index first. So the innermost loop always has to have the leftmost index first as the fastest. In C, it's exactly the opposite, it's the rightmost index. In NumPy, by default, is the rightmost index, I think. I'm actually not sure. I haven't, as you can see, I haven't written too many performance critical code in NumPy itself. NumPy allows Fortran and C order. I just don't remember right now, to be honest, which order is the C is the default, but I don't know the order of the arguments. But in Fortran, yeah, it's always it's the contiguous. And so anyway, once you learn these little tricks, it just opens up, a lot of possibilities. So I'm sure we don't know what else we are missing. So we see Fortran, we have the array, so I know we want that. But what else do we want? Until we have it and have some experience with it, we don't know what we are missing. And so I think no doubt we are, I would say, with parallel features. I think, so Fortran has parallel arrays, but I feel there is more that can be done on the language level in terms of parallelism. But until we have it, it's hard to, hard to know what we are missing. But I think it's another example that things might change a lot in the future if language is become, as they introduce these features, it will just enable all kinds of easier programming. So I would say yes.
Thank you. So regarding the multidimensional arrays, so people like us who have to spend professional time with tensors, I think it's a very, I'd say, comfortable world out there, which I think I'm missing out on because I'm not using Fortran. Well, we have this to a certain extent in other languages, but I think it lends itself naturally to that kind of thought process. People who think about tensors and as theoretical phases, I think you can appreciate it much more than I do. So the entire the Einstein's index notation, you keep on just putting on the subscripts, and then you have a nice, very structured mathematical way of condensing the entire thing without losing your mind.
Yeah, and I guess I'm used to using tensors in the physics sense, which are, so it's about the transformations and the bases and the coordinate bases and so on. So it's a coordinate-free representation of the equation.
Yeah.
But the multidimensional arrays, I like to call them arrays because it's just a set of numbers, but it's just a convenient way of organizing instead of storing every, what I described in that example, instead of storing it as separate arrays, or not even arrays at all, sometimes it's just computation. It's easier. Well, it might sound more messy to just store everything in one array or a couple arrays, but if you do it well, first of all, it's extremely performing because the data is contiguous in memory, and the compilers can really do a good job optimizing it. But also, it's actually simpler to read also because the code is just kind of shorter, and you still use the indices to distinguish between the different things. So it's just for perform, and you have to do it anyway for performance code. Even if you don't want to think of it as a multidimensional array, you want to have the data in memory in a contiguous way, and you need to be able to access it, optimize the accesses to memory. And so you might as well use multidimensional arrays. It gives you structure to the code. So I think it's not really that complicated.
Do you think that like physical objects having multiple degrees of freedom, they could be encoded in this way? Probably it's already done. I'm not experienced enough to know.
Are you thinking like pendulums or like
change?
So if you do if you want to store the coordinates, so depends what coordinates you choose, but whichever way.
And not just the coordinates, well, the information that you need for each point. So maybe the velocity and the position. So all of them together in a bunch of together as a multidimensional array.
If you write a molecular dynamics code, so you store all the particles in the array, all the coordinates and the speeds in the 2D array. Like one index is the XYZ dimension, and the second index is particle index. Yeah, but you have to do that.
Yeah. All right. So I think, by the way, I didn't ask you about your recent new job. Congratulations about that. You are now no longer in Los Alamos. You're at GSI Technology. Do you want to end this discussion with a little bit of description of work that you're doing?
So I really want to finish this LFortran compiler. And so I think, I don't know if it's because most people are, these big, companies are moving away from Fortran or what it is, but it was hard for me to get funding. I did find some. I was very happy about it, about 30% of my time. And I'm very grateful for that. But I really wanted to focus 100% on this. And so I found this company called GSI Technology. It's a hardware company. They develop chips, and they're mainly, their business is selling memory chips, but they also recently started developing their own, actually like a computational chip, computing in memory, and it's much faster than a CPU for certain tasks. And so, but it has a very peculiar, their own, new architecture, and so they wanted to make it easier for people to program, and so they have a compiler team. And they liked the LFortran design, and so I decided to join them. And so I'm now a compiler developer full time, working on using the LFortran middle end and the backend. They don't mind Fortran, but as we discussed, Python is the most kind of the first language that needs to work, and so we are also writing a Python front end to the same middle end that LFortran uses, and so I'm now working pretty much on this compiler, this compiler technology full time, and so I'm very excited about it. It's and also we have funding for students. So if any of you are interested listening, and if you are interested in working with us, let me know. Just contact me.
So when you mentioned that you are interested in working with students, do you mean in the form of internships?
Internships, and you don't even have to be a student, but yes, internships. And other opportunities.
I believe our students would love this part of the conversation.
Email me if you're interested. Email me.
All right. Okay. So let's end this discussion on this very positive note, very helpful note. Thank you, Ondrej, for sparing your time. I have overshooted. Well, is this not even overshooting? This is massively overshooting the time. But thank you so much indeed.